A very good morning to you. Principles of Geochemistry, Principles of Crystal Structure, Lecture 6. Coming to the contents of this topic, it includes the introduction, principles of crystal structure, types of chemical bonding, crystal field theory, and summary. Principles of crystal structure. The basic unit in all the crystal structures is the atom. This may be associated with the other atoms in a group behaving as a single unit in the structure. We may consider atoms as being made up of electric charges which are distributed through a small sphere that has an effective radius of the order of 1 Armstrong unit. And 1 Armstrong unit is denoted as 10 to the power of minus 8 centimeter. The radius measure, it depends not only on the nature of the element, but it also depends on its state of ionization and the manner in which it is linked to adjacent atoms. Suppose if we take the radius of sodium atom. Radius of sodium atom in metallic sodium is 1.86 Armstrong units. But the radius of the sodium ion in sodium salts is 1.02 Armstrong units. Number 2, bonding. The different kinds of interatomic linkages are classed into 4 bond types. These are represented as metallic bond, ionic or polar bond, covalent or coordination bond, and residual or Vanderwaals bond. Coming to the metallic bond is responsible for the coherence of a metal, and the ionic or polar bond, which is nothing but the linkage in the salts such as sodium chloride. And the covalent or coordinate link or coordinate bond, this is present in the crystals such as diamond, and the residual or Vanderwaals bond, which is responsible for the coherence of the inert gases when condensed to solids at low temperatures. And these 4 types of bonds, they all impact characteristic properties to the substances in which they occur, and they provide a convenient basis for the classification of crystal structures. When more than one type of bond occurs in a single compound, then they are known as heterodesmic. The physical properties like hardness, melting point, mechanical strength, so these are determined by the weakest bonds, which are the first to suffer by disruption under stress or under pressure. Homodesmic means if only one bond is present, then they are termed as a homodesmic. Then according to the crystal field theory proposed by Burns in 1970, divalent ions of titanium, vanadium, chromium, iron, cobalt, nickel, and copper, they receive a stabilization energy in octahedral sites, whereas manganese, zinc, and non-transition elements of the similar size, they do not receive stability, and hence the concentration of iron, cobalt, and nickel, they occur in the lower mantle. Coming to the first rule of the crystal structure, for elements in the same group of periodic table, the ionic radii increases as the atomic number increases. Suppose if we take the group 2 of alkali earth metals, so the beryllium atomic number 4 and it has the ionic radius 0.27. Magnesium, it has an atomic number 12 and it has the ionic radius 0.72. Calcium, atomic number 20 and its ionic radius is 1. Strontium, atomic number 38 and it has an ionic radius of 1.13. Followed by barium, it has an atomic number of 56 and the ionic radius is 1.36. So, as the atomic number increases, the ionic radius increases. Coming to the second rule, for positive ions of the same electronic structure, the radii decreases with increasing charge. Coming to the second row in the periodic table, which will have 2 electrons in the outermost orbit, if we go across a row in the periodic table, the radii of the ions decreases. As the electrons are lost, the nucleus exerts a greater pull on the remaining, thus there is a decrease in the effective radius of the ion. So if you take sodium Na+, it has an ionic radius of 1.02. followed by magnesium Mg2 plus, it has an ionic radius of 0.72, aluminum 3 plus, it has an ionic radius of 0.53, and silicon plus 4, it has an ionic radius of 0.4, and phosphorus 5 plus, it has an ionic radius of 0.17, and sulfur 6 plus, it has an ionic radius of 0.12. Coming to the third rule, for an element that can exist in several valence states, that means from ions of different charge, the higher the positive charge on the ion, the smaller is the radius. So if you take an example of Mn2 plus, Mn2 plus, it has an ionic radius of 0.82, and Mn3 plus, it has an ionic radius of 0.65, and Mn4 plus, it has an ionic radius of 0.54. So the loss of electrons, it causes the remaining electrons to be more strongly attracted by the nucleus, and hence contracting the outer electron orbits and decreasing the ionic radius. Coming to the fourth rule, as atomic number increases, there should be increase in the radius, but there is decrease in the radius. This is an apparent contradiction to the first rule, which is provided by the rare earth elements. This remarkable feature is known as lanthanide contraction. The trivalent ions of these elements decrease in radius, so that is lanthanum 3 plus, it has an ionic radius of 1.14, and followed by lutetium, it has an ionic radius of 0.85. This is due to building up of an inner electron shell instead of adding a new shell. As a result, the increasing nuclear charge, it produces an increased attraction in the outer electrons and an effective decrease in the ionic radius. So this remarkable feature is known as lanthanide contraction. Coming to coordination number. Coordination number of an atom in a molecule is the number of its nearest neighbors. And high temperature, low pressure, it favors low coordination number, whereas low temperature and high pressure, they favor higher coordination number. For example, if we take aluminium in high temperature minerals, it occurs in fourfold coordination number. It substitutes for silicon, whereas the aluminium at low temperature, it exhibits sixfold coordination. And high pressure form of silica is stishovite, which is a polymorph of silica. And here is silica, it occurs in sixfold coordination. Radius ratio. Radius ratio is the radius of the cation by radius of anion. And here you can see the arrangement of anions around the cation and the coordination number of the cation. The table, it represents the relationship between radius ratio and coordination number for ions as rigid spheres. If the radius ratio is 0.15 to 0.22, then the arrangement of anions around the cation will be the corners of an equilateral triangle, and the coordination number of the cation is 3. If the radius ratio is 0.22 to 0.41, the arrangement of anions around the cation will be in the corners of a tetrahedron, and the coordination number of the cation is 4. And if the radius ratio is 0.41 to 0.73, the arrangement of anions around the cation is in the corners of a octahedron, and the coordination number of the cation is 6. If the radius ratio is 0.73 to 1, the arrangement of anions around the cation will be in the corners of a cube, and the coordination number of the cation is 8. If the radius ratio is 1, the arrangement of anions around the cation will have the closest packing, and the coordination number of the cation will be 12. Coming to the summary, the basic unit in all the crystal structures is atom, and the radius measure, it depends not only on the nature of the element, but it also depends on its state of ionization and the manner in which it is linked to adjacent atoms. And the different kinds of interatomic linkage are classed into 4 bond types as metallic, ionic, covalent, and Vanderwaals bond. And if there are more than one type of bond occurs in a single compound, then it is known as heterodesmic. And if only one bond is present, they are known as homodesmic. For elements in the same group of periodic table, the ionic radii increases as the atomic number increases. For positive ions of the same electronic structure, the radii decreases with the increasing charge. For an element that can exist in several valence states, that means from ions of different charge, the higher the positive charge on the ion, the smaller is the radius. And as the atomic number increases, there should be increase in the radius, but there is a decrease in the radius. This remarkable feature is known as lanthanide contraction. And coordination number of an atom in a molecule is the number of its nearest neighbors. High temperature, low pressure, it favor low coordination number, and low temperature and high pressure favor higher coordination number. Radius ratio is radius of cation by radius of anion. Hope you have followed the content. See you in the next video. Hope you can explore geosciences and subscribe. Thank you for your time. See you in the next video.